Hello, my name is Noel Thompson. I am from Arkansas Nuclear One, and I am the Community Engagement Liaison. And today I'm here to talk to you about nuclear energy and you, and the impact nuclear energy has on your health. So, a brief outline on the presentation I'm going to be giving you today. For people outside of the scientific community, nuclear power can be somewhat complicated. There can be quite a lot of overwhelming information available, so I'm just briefly today going to go over the basics of how nuclear power works, a brief history on how it was developed, and the overall effect on the environment and public health concerns. In addition, I'm going to talk about how we regulate and monitor levels, and hopefully assuage any concerns that you might have about the possibility of a catastrophic event happening here in Russellville. So when I was growing up in Oak Ridge, Tennessee, which is home to a nuclear processing facility, there was a saying about the locals that we used to glow in the dark. Obviously we don't, but the generalization highlights that there are key misconceptions about nuclear power and its utilization. Here I've highlighted some of the most frequent questions I hear about nuclear power on a day-to-day basis. For instance, why do we use nuclear power and how does it work? One of the main concerns about living or moving to a community with close proximity to a nuclear power plant are the repercussions on family and individual health. So how does this affect our health? So what risks are involved in living near the plant? Are there risks involved in living near the plant? In the case of a large-scale meltdown, what do we do and what's being done to prevent this? Before discussing nuclear energy and health, I want to briefly go over the inception of nuclear power and how it became so prevalent. So in the late 1800s and the early 1900s, famous scientists you might have heard of, like Marie Curie and Ernest Rutherford, began studying specific elements that had unique features. These elements naturally gave off a specific type of energy. This is later coined as radioactive energy or radioactivity. It was later discovered that by bombarding these elements with protons, it led to a heat-generating process known as fission that gave off a lot of energy. After this power was demonstrated during World War II in Japan, an effort was made to harness the process for fuel during peacetime. The first experimental reactor was known as EBR-1, and it was located in Idaho. It was demonstrated that this was possible to be sustained on a small scale. It wasn't until 1957 that the first commercial plant opened in Shippingport, Pennsylvania, and this led to the proliferation of over 100 reactors today in the United States, which generate 20% of our total electricity. This is only third behind coal and gas. So as you can see from the map, Arkansas is home to 2 nuclear reactors, which we have here in town, and we know this as Arkansas Nuclear 1. Both reactors are pressurized water reactors and are here in Russellville. The first reactor went into operation in 1974, and the second reactor went into operation in 1980. Arkansas Nuclear 1 supplies 60% of the total energy on demand of Entergy's commercial and residential customers in Arkansas, and employs more than 900 full-time workers to assist in daily plant activities. So, we hear about nuclear reactors producing energy, and we hear about nuclear fuel, but how does it specifically work? In reality, this process is very similar to how a hydroelectric plant works. So nuclear fuel, which is often uranium or plutonium, is mined, refined, and processed into a stabilized form of energy, which we call a fuel rod. So these fuel rods are placed in the core of the nuclear reactor, as you can see in the diagram, and they're surrounded by a closed water system. The fuel in these fuel rods are constantly undergoing fission and giving off this energy in the form of heat, and they heat the water to very, very high temperatures. So this hot water heats a separate closed water loop, so they're separated, and it changes the second closed system into steam. This steam goes through a tube, which rotates a turbine, and that turbine works against a gradient and generates an electricity for commercial use. If there's a need to stop the process, control rods can be inserted in between the fuel rods to slow the process of fission. This entire processing is encased behind thick concrete and steel protectors in case of an uncontrolled reaction that could potentially lead to a meltdown. And this is going to be discussed in depth later on. So as we saw in the previous slide, the byproduct from nuclear power is only spent fuel rods. In comparison, fossil fuels have a variety of byproducts that have an immediate impact on your health. So these pollutants include carbon dioxide, which is one of the main contributors to global warming and the greenhouse gas effect, sulfur dioxide, which produces acid rain, and a variety of nitrous oxides, which contribute to ozone degradation and smog. So annually, also, occupational hazard-wise, there are far fewer deaths in nuclear energy than these carbon-based fuels, and nuclear energy contributes 0 harmful emissions in the atmosphere. One of the main drawbacks that we have is what to do with these spent fuel rods after we've used them. So if they're no longer viable for energy production, what can we do with them? So what about the effects of local radiation? So let's say you get a large-scale dose of radiation immediately. Doesn't it have a greater impact on humans than burning fossil fuel? The answer is yes, but it's very unlikely to happen. So let's talk about it. So this chart outlines various levels of exposure and the impact that they have on your health. Radiation is measured cumulatively over the course of your life in a unit known as a REM. This used to be called a sievert. As you can see from the graph, the majority of the U.S. population falls within the tolerable level, or the yellow and orange level. According to studies done by the International Atomic Energy Agency, individuals who live within a 50-mile radius, so that would be all of you, of a nuclear power plant are exposed to 0.01 millirems of radiation. So this is equivalent to an additional 1/1000th of a single chest x-ray, or the equivalent of eating a banana. It is not until a person accumulates over 50,000 millirems over the lifetime that your lifetime risk of cancer increases. And this is significantly higher than even the peak exposure of radiation that plant workers working in the aftermath of the Fukushima meltdown received. It should be noted that your average yearly radiation for an average U.S. citizen is 620 millirems per year, or the equivalent of 62,000 times that of your annual radiation from living within 50 miles of this power plant. So the majority of radiation as an individual is due to your exposure to constant things like radiation being given off by the Earth or radiation from cosmic rays from the sun. If you are working in the air travel business, if you are an air stewardess, if you are a pilot, this slightly increases. If you're closer to the sun, if you're higher in altitude, this also increases. But generally, we don't have to worry about radiation as measured from living this close to a nuclear power plant. So before this slide, I want to extrapolate on how we generate test data for the effects of radiation on health. So ethically, we can't fire radiation at humans. We can't have ionizing radiation going at humans for the sake of scientific testing. So the majority of the data that we do have on radiation's impact comes from data gathered after the nuclear weapons were dropped on Hiroshima and Nagasaki during World War II. When identifying these risks, there are cases of extreme exposure over a short period of time. So what about particularly susceptible populations, such as children, the sick, or elderly? What does a sustained dose of annual radiation do? As mentioned earlier, the effects of radiation is cumulative and only shows up over a long period of exposure. So think of over 50,000 millirems over the course of your lifetime. As such, unless the exposure to a radiation source is prolonged and extreme, so immediate exposure to fuel rods over a course of a significant period of time, there's still a very similar risk level in comparing the sick and the elderly populations as compared to the normal populations. However, children fall in a different category. A 2013 report published by the UN Scientific Committee on the Effects of Atomic Radiation, or UNSCEAR, as seen here, in reference to the Fukushima nuclear power plant disaster, found that extreme doses received by children and adults from the same source of ionizing radiation can actually have different impacts. Specifically, children are more susceptible to leukemia, thyroid cancer, brain cancer, and breast cancer later in life, due to biological and physiological difference between adults and children. So how do we know the amount of radiation present? So we're worried about this. How do we know we aren't receiving unhealthy levels of radiation on a daily basis? Who's ensuring that we're making sure we have proper levels of radiation? So there are actually many different bodies of organizations that oversee this process and make sure that we're not getting damaging amounts. So when dealing with radiation, the initial standards and guidelines are developed by the Environmental Protection Agency, so the EPA. And they also have an administrative role in this process as they assess the impact of radiation in the environment. The regulations are then enforced by the Nuclear Regulatory Commission, which monitor the use of nuclear materials at power plants in the United States. And after the fuel is used, the Department of Energy oversees its transportation and getting rid of the spent fuel. And in the case of large-scale emergencies such as natural disasters or terrorist attacks, the Department of Homeland Security has preparations in place for emergency responders, and they also educate the public on preparing for other major emergencies. So now that you understand how nuclear energy works here at Arkansas Nuclear One, let's talk about the impact nuclear energy has on the environment. So oftentimes we hear nuclear and environment used in the same sentence, and we think of catastrophic events such as Fukushima or Chernobyl, and those are certainly events that we need to consider. But on the local scale, how does nuclear energy impact our wildlife or our water? Globally, we are worried about the type of radiation that may be leaking into the environment. What contaminants are going to the soil or land that may transform the land, and how do we evaluate this to ensure that we're making sure that the nuclear power plant isn't affecting the environment and later affecting ourselves? Environmental monitoring is done on an annual basis to evaluate for these abnormalities and to ensure safety in environmental conditions. Every year, the Nuclear Regulatory Commission releases an annual radiological environmental operating report. This report uses a standardized system to evaluate radiation levels done by sampling air, sampling the water, sediment, fish in the water, and food products, as well as measuring radiation directly. This is done within a 20-mile radius of the plant and specifically uses indicator locations to evaluate the impact. In the last report, published in 2016, radioisotopes and radioactivity across the board were either at undetectable levels or well below the reporting limit set by the EPA. This report is available for viewing on the National NRC website if you're interested. One of the more interesting methods of measuring radioisotopes in relation to human activity that we use is through evaluating local milk sources. There are two primary reasons for this. First, if radioisotopes harmful to humans are present in the surrounding land, this will show up fairly rapidly because the cows are eating the grass. The radioisotopes from the grass are then translated into the cow's milk, and we find it in the cow's milk. Second, the main consumers of milk are children. It's obvious that the milk is unsafe for consumption. If that's the case among this population, we want to catch it early to avoid any complications long-term and complications that may not show up in adults. There are several well-known incidents of total or partial nuclear meltdown in history, but I wanted to briefly discuss the two major events that are well documented. In 1986, Chernobyl was the site of a USSR nuclear plant. Scientists wanted to do a test to see if the turbines that generated electricity could produce enough electricity to keep coolant running into the core in the case that there was a total power loss if everything shut off. However, the only way to accomplish this was to turn off the safety systems. The resulting power failure and the inability to shut off the reactor resulted in a buildup of a massive amount of steam that resulted in an explosion. However, a further study found that the operators hadn't been violating any operating procedures because of their actions, because there simply just weren't any procedures and policies to prevent this in existence. This led to the creation of many more policies and regulations in low power use and improved designs. Today, computer simulations can help answer these questions that we have about low power systems, so we're no longer in the need to have to turn off these safety systems for these tests. More recently, in 2011, you may remember that the Fukushima core meltdown followed a 9.0 magnitude earthquake, and there was a subsequent 50-foot tsunami that flooded the power plant. The reactors actually sustained the earthquake, but lost emergency power when the site was flooded by the huge tsunami wave. Water that was normally pumped in to cool the core from the Pacific Ocean couldn't get access, and the meltdown occurred in the core. So in response, the Japanese decided to directly flood the core with ocean water that flowed directly back into the Pacific and contaminated the Pacific Ocean. So what are the odds of something like this happening in Arkansas? The NRC did a study in 2010 to calculate the odds of an earthquake reaching the threshold for core damage in all national plants, and found that Arkansas's odds were 1 in 286,000 based on geological data. Interestingly enough, no data was available for tsunami risk in Arkansas. So the worst case scenario for Arkansas Nuclear 1 would be what's called a meltdown, where the fuel rods create an uncontrollable chain reaction, reaching a temperature so hot that the core would literally melt. This would leak the radioactive isotopes into the containment area and hypothetically into the area outside. This has never happened in Arkansas and last happened and only partially in the United States in 1979 at 3 Mile Island. As mandated by the Nuclear Regulatory Commission, there's a plan in place for all counties within 10 miles of the plant, designed by the Arkansas Department of Health. In the case of a nuclear event, a siren will immediately go off, and if you hear the siren, turn on local radio or news stations and listen to the information being distributed. They may or may not require an evacuation of the area based on severity of the incident. This map shows the evacuation route for the 5 to 10 mile radius are the area most susceptible to the effects of radiation in the immediate aftermath of a nuclear event. The routes are noted by blue signs labeled Nuclear 1 Evacuation Route. So in summary, nuclear energy is much healthier on an environmental and public health basis than carbon-based coal. There's insufficient evidence to suggest that local exposure as a resident is linked to any adverse health outcomes. Significant oversight and redundancy policies and procedures ensure safety when you're dealing with these nuclear materials. In extreme cases of these nuclear exposure do increase risk of some types of cancer, but as you've seen, these occurrences are very rare. And in the case of these emergency situations, Arkansas has guidelines and procedures in place. Here's a list of some of my citations. This is a continued list of my citations. Thank you so much for letting me come in and talk to you. If you have any questions, feel free to contact me. Once again, my name is Noel Thompson. I am the Community Engagement Coordinator and Liaison here at Arkansas Nuclear One. Thank you so much.